Have you ever wondered how the exact same technology used for incredibly delicate eye surgery can also slice straight through massive slabs of solid steel? Well, let's dive right into this fascinating journey from microscopic precision to the absolute brute force of industrial metal cutting. Welcome to today's Explainer, where we're going to tackle a massive question that is completely shaking up heavy manufacturing right now. How do modern lasers actually compare to traditional plasma cutters when it comes to cutting thick metals? Have lasers finally dethroned plasma? Let's let the data and the science tell the story. Now, to make sure we don't get whiplash jumping from human corneas to 50-millimeter thick steel plates, here is our roadmap for today. We've got 1. Anatomy of a laser. 2. From medicine to manufacturing. 3. The fiber laser revolution. 4. Showdown, laser versus plasma. And 5. The business of cutting. All right, let's jump straight into section 1, anatomy of a laser. So to really get this, we have to zoom all the way down to the atomic level. Did you know that laser is actually an acronym? It stands for Light Amplification by Stimulated Emission of Radiation. It's basically a description of an exact quantum process where optical materials absorb energy, like from an electrical current, and that energy excites their electrons, bumping them from a lower energy orbit right up into a higher energy orbit. And here's where the quantum physics gets really cool. When those excited electrons naturally drop back down to their normal ground state, they release that extra stored energy as tiny particles of light, which we call photons. But what makes a laser so special is that these photons bounce back and forth between mirrors inside what's called a gain medium. This bouncing actually stimulates the emission of exact clones. They align perfectly. Imagine a perfectly synchronized marching band in a parade, all stepping in unison at the exact same wavelength. That coherent unison, that's exactly what gives a laser its immensely focused cutting power. Moving right along to section 2, from medicine to manufacturing. Now that we know how this synchronized light is made, how do we actually use it? Well, depending on the specific gain medium used to amplify the light, lasers generally fall into one of 5 main categories. You've got your gas lasers like CO2, solid-state lasers using crystals, fiber lasers that use silica glass, liquid dye lasers, and semiconductor laser diodes. And the crazy thing is, each one of these is suited for entirely different real-world tasks, from scanning your groceries at the supermarket all the way to heavy industry. To really appreciate just how precise this light can get, let's look at the medical field for a second. This number right here, $2,250, is the national average cost per eye for LASIK. That is a highly elective surgery relying on the extreme, pinpoint precision of ultraviolet excimer lasers to physically reshape a living human cornea. Now, you might be wondering, how on earth do you shoot a laser into someone's eye without literally cooking it? The secret is in the pulse. By using ultra-short nanosecond or even femtosecond pulses, these medical lasers can vaporize exactly 0.25 micrometers of tissue per pulse. The pulse is just so incredibly fast that the heat literally doesn't have time to spread. As you can see, a 10 nanosecond pulse results in just 37 nanometers of thermal damage. That safely prevents harmful heat from spreading to the rest of your eye. Okay, let's scale this up in section 3, the fiber laser revolution. We're shifting from the operating room to the factory floor because there has been a massive recent shift in how we generate laser power. What's truly revolutionary right now is the advancement in single-emitter pump diode technology. The electrical efficiency of these diodes has absolutely skyrocketed, from a measly 20% to roughly 70%. At the same time, the raw output power of a single emitter has jumped by several orders of magnitude. This means the cost per watt has been driven down by a massive factor of 100, all while making the equipment last much longer. Thanks to these crazy efficiency boosts, better beam delivery, and way better thermal management, we are long past the days of just delicate eye surgery. We now have continuous wave fiber lasers pushing well past 100 kilowatts of raw industrial power. It's a total game changer. Which brings us to the main event, Section 4, Showdown, Laser versus Plasma. With this massive scale-up in power, we really need to look at how these modern high-power lasers stack up against traditional plasma cutters for thick metals. For decades, conventional wisdom just flat-out dictated that lasers were only for thin sheet metal. The belief was that if you needed to cut mild steel over 1 inch thick, so about 25 millimeters, plasma was the undisputed, unbeatable king. But let me tell you, that wisdom, it is incredibly outdated today. Just look at this current performance data, it literally changes everything. When we're talking about mild steel that is a whopping 40 millimeter stick, that's over an inch and a half, a 60 kilowatt fiber laser is clocking in at about 0.75 meters per minute. Now, compare that to a massive 460 amp plasma cutter sitting at roughly 0.3 meters per minute. The modern laser is cutting 2.5 times faster than the plasma cutter on thick steel. No way around it, that is huge. So, what's the secret weapon behind this incredible speed? Well, it isn't actually just the raw power of the light itself. Modern systems use highly optimized assist gas delivery. By utilizing a mixed assist gas, mostly nitrogen with just a little bit of oxygen, the system efficiently blasts the molten material right out of the cut. That's what allows for those blazing fast speeds and incredibly clean edges, even on thick slabs. And this dynamic explains exactly why lasers used to struggle so much with thick metal. If your laser is underpowered, say under 30 kilowatts, you're basically forced to use pure oxygen so the cut doesn't stall out. But pure oxygen slows things down and creates a much lower quality edge. But once you scale up past that 40 kilowatt threshold, you can finally utilize that mixed gas. The result? Faster speeds and perfectly clean dross-free edges that are often totally weld-ready. No extra grinding or post-processing required. All right, let's wrap things up in section 5, the business of cutting. So the ultimate question is, how do these impressive physics and speed metrics actually translate into cold, hard cash on the factory floor? The economics are honestly staggering. If we compare a 40 kilowatt fiber laser to a 300 amp plasma cutter working on 20 millimeter thick steel, both systems cost roughly $20,000 a month in electricity, labor, and consumables. However, because the laser cuts at 8 meters a minute versus plasma's 4 meters a minute, the laser churns out 38,000 meters of product a month. The plasma cutter only hits 19,000 meters. For the exact same operating cost, the laser is literally giving you double the output. Let's follow that math through, because it's fascinating. If a factory needs to produce 38,000 meters of cut steel a month, they only need one laser, costing $20K a month to run. To hit that exact same goal with plasma, they'd need 2 whole machines, doubling their monthly running costs to $40,000. So even if that single laser costs a massive $400,000 more in upfront capital to purchase, the $20,000 in monthly operating savings pays off that premium in just 20 months. From then on, it is pure profit. So when does it make sense to finally ditch plasma and go all in on a high-power laser? Well, if your manufacturing line requires intricate geometries, if you need clean edges to skip post-processing labor, if you need a smaller machine footprint, and most importantly, if you have the sheer production volume to keep the machine busy, the fiber laser is fundamentally the clear economic winner for thick metals. When you step back and look at the big picture, it really is amazing. To think that the exact same quantum physics principles used to delicately reshape a human eye with microscopic precision are now effortlessly slicing through solid blocks of industrial steel. Lasers have definitively crossed the threshold. They aren't just light-duty tools anymore. They are the new kings of heavy manufacturing. With powers now pushing well beyond 100 kilowatts, it leaves us with one incredibly fascinating question. What massive industry will perfectly synchronized light conquer next?